And I'll give you a moment to copy this example down. And regarding homework questions, I generally like to cover those at office hours. But after class, Marcus, we can, if you know how we can meet after class to right after. I can help you with your questions. That's that cool? Is that okay? Excellent, excellent. Okay, so, all right. Now, you have had some experience with partial fraction expansions for solving an integral. Hold on, let me get my email off here. I don't want any distractions. Okay, good, good. Okay, so in this problem, let me ask you, what is the degree of the numerator? The polynomial, good, it's third degree. That's right, Samuel. And in the denominator, what's the degree of that polynomial? Good, Jacob, also third degree. So when that happens, okay, in that kind of situation, and they talk about it in the book, they have like after in section 5.7 after example 4, they have a note saying that if the degree in the numerator is the same as that of the denominator or higher, then you have to perform long division first. So in this problem here, you have a numerator and denominator with the same degree. They're both third degree. And you can't do partial fraction, you can't like factor the bottom and do partial fractions and have it work. For the partial fraction expansion, you want the numerator to be of a degree less than the denominator. So we're going to divide the function on top by the function on the bottom. How many remember in pre-calculus taking polynomials and dividing them by polynomials? Okay, Marcus remembers that. And hold on here. Marcus remembers that. Wait, who else here? Let me just hold on here. Let me get my Thomas does and Jacob does. Okay, so let's go to the next page. So what I've done is I have an analogy here. Before I do my division here of the numerator divided by the denominator, you know, here's the numerator, here's the denominator. I want to remind you that that division is no different than the division you learned in grade school. Like for instance, let's say you had the fraction 20 over 3, 20 thirds. Okay, well 20 divided by 3, okay, is 3 goes into 20 6 times. 6 times 3 is 18, you have a remainder of 2. So 20 over 3 is equal to the quotient 6 plus 2 thirds, right? After all, 6 is equal to 18 thirds, right? So 18 thirds plus 2 thirds is 20 thirds. Okay, so the same process here for dividing a number by a number we do with the polynomials. So the numerator here, okay, x cubed minus 2x squared minus 4, I write that as x cubed minus 2x squared plus 0x minus 4. You know, I like to have my placeholder in here. I want a 0x there. Okay. And I focus on the x cubed here, and then in the denominator that I'm dividing into the numerator, I focus on the highest power as well. X cubed goes into x cubed one time. 1 times x cubed is x cubed. So what I do is I multiply 1 by x cubed minus 2x squared. That gets me x cubed minus 2x squared, and then I subtract. Right? I subtract that. Just like I subtracted here with the little easy example, right? Well, what happens is when I subtract, I get a -4. And so this means then that my integral here, hold on here. And remember, you can click on, there's a zoom feature on the right side of your viewer that allow you to blow this page up if you want to make it higher, magnified more. So it turns out that it turns out that x cubed minus 2x squared minus 4 divided by x cubed minus 2x squared, it turns out that's going to equal 1 minus the remainder 4 over x cubed minus 2x squared. No different than what we did here with the simple problem, you know, where we, you know, the grade school problem where we did division. It's the same procedure. So are there any questions, you know, up to this stage here? Are there any questions at all? Yes, Baraka.
Wait, so where did the 1 come from? Is that from x cubed over divided by x cubed?
That one is this one. So I'll show you an analogy here. Okay, your question's good. So let's go back to the simple problem here, the grade school problem. So you know, here's the 6. I brought it down, and then 2/3 is here, right? So you're comfortable with that, Baraka?
Okay, yeah, that makes sense. Yeah.
Okay. So same thing here, same situation here. Here's a 1. That's there. And then I have a remainder of -4 over, let me maybe put that in red. I have a remainder of -4 over x cubed minus 2x squared. And there's 4, well, there's -4, should be -4, right, over x cubed minus 2x squared. Okay, does that help you feel a little more comfortable?
Yeah, thank you.
Okay, you're welcome, you're welcome. And so now I'm ready to roll, I'm ready to go. I'm gonna, you know, I have the integral of a difference of 2 functions. I'll write that as the difference of the 2 integrals. And now of course, the first integral is easy to do. The second integral is a little more challenging. But what method am I going to use to evaluate this second integral?
Substitution.
Well, if let's say I let u equal x cubed minus 2x squared. Actually, hold on. I'm gonna do that just for the moment. Okay. Let's say. And then hold on, Jacob. I'll be right with you. One moment. Let me plug this. Got to plug my thing in here. One moment. Okay, so if I let, hold on here, let me do this. Okay, so let's focus here. If, now don't write this down, if I let u equals x cubed minus 2x squared, then du is going to equal 3x squared minus 4x dx, right? But in the integral here, here's x cubed minus 2x squared, there it is. But, and that would be the u, but the problem is the 4dx here, I can't get that replaced with this here. So substitution isn't quite good, isn't going to work. It isn't going to work. But good try, Samuel. Good try. What other approach? Oh, well, now Sean's saying partial fractions. Okay, I like partial fractions because it's a, I mean, what do we have here? We have a rational function, and we use partial fractions a lot for rational functions. And what do you notice about the denominator? The denominator can be what? The denominator can be
distributed.
That's right, can be factored. And so, okay, well then let's go to the next page. Then if everybody, is everybody good so far? Okay, Sean's good, something's good, great. All right, here we go. So, okay, I'm going to factor the denominator here. And the thing is, I have x squared times x minus 2, but the x squared I can write as x times x. You see, I want to completely factor the denominator out. And I get what's called a repeated linear factor, because x squared is x times x. You know, I mean, this is completely factored, right? There are 3 factors in that denominator. 3 factors, an x, another x, and an x minus 2. So what's the partial fraction expansion going to be? Well, this is kind of interesting. So you know, I have in the denominators, I have x, okay, and then I have x squared and x minus 2. So this is a little different, right? You might think here I should have an x, but it doesn't work that way when you have a repeated linear factor. When you have a repeated linear factor, you write the x and then the x squared, okay, and then you have the x minus 2. So that's how you do it when you have a repeated, what's called a repeated linear factor. Okay, so like for instance, as an analogy here, let's say instead, let's say you had 4 over x cubed times x minus 2. Let's say you had that. Okay, what do you think the expansion would be for 4 over x cubed times x minus 2? It's going to be a over x, Jacob, yep, plus
b over x squared.
Plus b over x squared, plus
C over x cubed.
c over x cubed, and then finally d over x minus 2. So that's the partial fraction expansion for when you have repeated linear factors. That's the pattern. That's the pattern. And it's important that you haven't had any repeated linear factors yet in your work. You haven't had any because well, you just haven't. But now with the 5.7 exercises due on Thursday, you'll have a few where you have repeats. okay? And it's important for differential equations as well. You're going to have partial fraction expansions you need to do that involve repeated factors. Yeah, Jacob, question?
Yeah, would you do the same thing if, say, the x minus 2 was cubed? Would you also need that to repeat?
Yeah, absolutely. If you had if you had an x minus 2, like if you had an x minus 2, like if you had, hold on, I'll write it like this. Hold on, let me go. Let's say you had this. Hold on here, one moment. Let's say you had 4 over, and I'll be right with you, Sophie, 4 over x squared times x minus 2 squared. Okay? That would be, this is a square here. That would be equal to a over x plus b over x squared plus c over x minus 2 plus d over x minus 2 quantity squared. All right, Jacob, is that good?
Yes, thank you so much.
You're welcome. Sophie, question?
Hi, Professor. Two things. I was wondering if you could elaborate more what you meant by repeated linear factor, and also I'm having trouble following how you're doing the expansion.
So you're comfortable with the expansions that you've experienced already, like in the homework that you had already, right, for 5.7?
I just wanted to
Okay,
go over.
good. So I understand what you're saying. It's kind of like, wow, this is why is that true? It has to do with what's called linear independence of terms, but I don't want to get too deep. But let's first of all talk about this. So see, the x squared technically is x times x. So because the x occurs twice, you have a repeated factor. And when that happens, when you do the expansion, you have of course, above the x, you have an a, because x is of degree 1, polynomial of degree 1, so you put a constant a above it. But then, because x is a repeated factor, you have to have an x squared. That comes next, but you just put a constant above it. Okay, and that's the procedure that will work. That normally, right? More normally, when you have a polynomial of degree 2, you would put like ax plus b above it, right? But in this case, with repeated linear factor, you don't do that. You don't do that, and you can see, like in this up here, you see how I did that expansion there. Same kind of philosophy. So, and in the homework, you're going to have like some videos and things to help you feel more comfortable. But does that help a little bit?
Yes, thank you.
Okay, great. You're welcome. You're welcome. Okay, well, so naturally, we want to now solve for those constants A, B, and C. So I'm going to multiply both sides of that rational equation by the least common denominator, which is x squared times x minus 2. And you'll end up with this equation here. Okay, let me just. The stylus is a little harder to control, oddly enough. I don't know why, but you get that, right? And so I'm gonna now expand this on the right. So Marcus, with partial fractions, there are basically patterns that you recognize. And the patterns have to do basically with linear independence of terms. And like think of it like this. Okay, think of it like this. Think of it like this. And then we'll, so like for this step here, let's say that I, instead of the x squared here in the bottom, let's just say that I had an x. Think of it like this. Let's just say I had an x. So, you know, the factors are x times x times x minus 2. And then here are my, you know, here are those factors, x times x times x minus 2. Well, what could I do? What could I do with those two terms? A over x plus b over x. What could I do with those two fractions? Could I combine them?
Yes.
Yeah, and so it doesn't make sense to have that. So I have the x squared here. You see? To make it different. So you work, the homework, you'll work with this a little bit, and I think you're going to get comfortable. I think you're going to get comfortable with it. You will get comfortable with it. I promise you. I'm trying to keep your problems in the partial fractions. You know, we can get very complicated, but I'm trying to keep things simple. And if you learn some basics here, then you'll be well prepared when you move on to differential equations. Okay. All right. So now we'll move here. Question about the test. There's no. I don't normally have review sheets, Samuel, but if you click the view key for like you know, a web-assigned assignment after it's past due, then you do get practice another version available for every problem. If you can do your homework well, you should do well on the exam. Okay, I mean the exam, yes, you'll be seeing some quote new problems, but if you know what I mean. They're the kind that, hey, if you can do your homework well, you ought to be able to do those. I assure you. All right, so moving on here. Now we have good questions, Samuel. Here's your equation. We got to solve for A, B, and C. So I expand it out. Okay, and now. And you've done this kind of thing before. Okay. Sophie, you're good. I can't keep track if I always have to exit out I think that was from.
Sorry, I just forgot to lower my hand.
Oh, no problem. So 4 will equal a plus c times x squared. Well, 4 will equal the quantity a plus c times x squared plus the quantity negative 2a plus b times x, and then minus 2b. And based on that, based on the fact that the right-hand side of this equation, 4, must equal the left-hand side of the equation, I come up with that a plus c has to equal 0. Okay. Negative 2a minus b equals 0, and negative 2b equals 4. Okay, so I have 3 equations and 3 unknowns. Obviously, the third equation I can solve for b, and then that allows me to solve for a and c. And so I end up then with my integral being equal to what what we have at the bottom here. The negative 1 is equal to a. I mean, this is absolutely beautiful, right? The negative 2 is equal to b. And then 1 is equal to c. Okay, and so now I think there's hope on the horizon here to solve this. And this is the kind of work naturally I'll want to see for your exam, right? When you first submitted work. All right, are there any, well, I'll give you a moment here to let me know if you have any questions. All right, are we ready to move to the next page? Okay, Nicole is, and Jacob and Sean, very good. Jiazi, Liping, excellent. I guess I don't have to always repeat students' names, but I like to acknowledge that I recognize your input. So, okay, so how many integrals are we going to have to do here?
4.
4 altogether. That's right, Maria. Okay, so let's go ahead and do them. And notice that the limits do not change on our integrals with partial fractions. So for definite integrals, when we do partial fractions or integration by parts, the limits don't change. But when do limits change? When we do a substitution. Okay, because we're converting the integral from one variable to another variable in substitution. Okay, well, let's go to the next page here. Okay, here is our then integral. Our integral is now 4 integrals, combination of 4 integrals. And now it's just like, doing these are like little calculus 1 problems, all 4 of these integrals. Oh, question, Samuel? Yeah.
Why does 1 over x, is it possible that there's a negative missing in there?
Is it possible there's what?
A negative missing? Wait, hold on. Wait a second. Oh, did you just multiply everything by -1? Is that why it's now positive 1 over x and positive 2 over x squared?
Yeah, let me go back here. Good question, good question. I'll go, yeah, so this negative here, I distributed it to each term.
Oh, okay.
All right, very good question. All right, and so that gets me here. Now hold on, there's another good question. Let's see, Marcus. One moment. All right, so go ahead and let's finish the problem here, and then Marcus, I'll go back to that. Okay. All right. Very good. Very good. One moment here. Okay, so I think all of this is pretty, the antiderivatives, they're just your simple antiderivatives. This last one, 1 over x minus 2, The antiderivative of that is the log of the absolute value of x minus 2. If you differentiate the log of the absolute value of x minus 2, you will get 1 over x minus 2. You'll get that. In the end, this is going to be your answer. And WebAssign wants exact answers, and you know, like for your for certainly, you will always WebAssign wants exact answers, and I would want that on the exam as well. This is not one where you approximate with a decimal, this kind of problem. Okay, so are there any questions on this part here? Yes.
The negative x to the negative 1 right here.
Okay.
Is that from the oh wait, 1 sec.
Yeah,
You took the integral and then and then it became what? Negative everything over negative 1?
Well, what I did was so 2 over x squared.
Also, sorry for drawing on the.
Yes, that's all right. That's all right. That's the same as 2 times x to the negative second power. And the 2 here, that 2, there's that 2. And so what's left is to find the antiderivative of x to the negative second power. That's just negative x to the negative first power. It's the power rule in reverse.
I see. Okay.
Yeah.
Okay. Thank you.
All right. Very good. Very good. Okay.
Real quickly, at the end, how did it go from ln 4 over 3 divided by 2 to ln 2 over 3?
Oh, so right here, Marcus?
Yeah. No, at the bottom.
Oh, okay. Okay. Well, all right. Well, so at the bottom, if let's focus our attention on the log of 4/3 minus the log of 2. So let me ask you then, hold on, now maybe I have, oh, okay, yeah. What's the log of A divided by B equal to? Do you remember your log rules? The log
I
of
wrote it down, but no, I don't have it.
the log, all right, the log of A over B. That's right. That's right, Shiazi. The log of A over B is log of A minus log of B. So think of this as the log of A. Think of this as minus the log of B. That will get me the log of the fraction A over B, and that's how I got this here. All right, Marcus?
Oh, okay, yeah. Okay, yeah, thank you, I got it.
Sure, all right, excellent. And so we end up with this as our answer. All right, are there any other good questions? Okay,
Actually,
let me
wait,
just
yeah,
go.
wait, actually, wait. Sorry about that. I had one question.
Sure.
Can we rewrite? Can we just rewrite? Oh wait, we can't just rewrite the natural log of 4/3 over 2 as 8/3, can we?
Well, 4/3 divided by 2.
Like only, I guess, or I guess you multiplied both by 1/2, maybe, so it would be 4/6, maybe.
Well, 4/3 over 2 is like 4/3 divided by 2 is the same as 4/3 divided by 2/1. And so that equals then 4/3 times 1/2. And hence it has to be 2/3.
2/3. Oh, okay.
All right.
Oh, I was zoomed in and I didn't scroll down. That's my bad.
No problem. No problem.
Thank you, though.
You're welcome. And here, so the one student, I don't know, maybe it was Jacob, I forget who asked, but if you multiply, well, that's what we're doing here. How do we arrive at this equation here? You multiply both sides of this rational equation by the least common denominator. And so on the left side, you get a 1 and a 1, and you're going to distribute this least common denominator on the right side to each term. And then so after you do simplifications, you'll get these terms on the right. And that's how you get that. All right, so that's in the recording. And you might have to, put in an extra step where you do the multiplication, and you'll see it. You'll see it. All right, very good, very good. So let me stop the recording here. I'm going to stop the recording and with the partial fractions. You've seen now you have a good basic. You've seen some nice examples of partial fractions, and that'll be helpful for you in this class and in future classes like differential equations, Math 282. Let me stop the recording.